Good morning from a stormy Mr. Anderson's house. We're going to conclude the last of our electrochemistry lectures today, which will be the last for the year. Congratulations, you made it through almost. But we're going to focus on electrolytic cells in this presentation. So electrolytic cells, again, are the non-thermodynamically favored processes. They are processes that will require an external power source in order to create that electrochemical cell. In this video, you'll learn how to calculate the amount of charge that flows based on the changes in the amounts of reactants and products in an electrochemical cell. We'll use Faraday's law to determine the stoichiometry of a redox reaction occurring in an electrochemical cell with respect to the number of electrons transferred, the mass of the material deposited on or removed from an electrode, the current, the time elapsed, and the charge of the ionic species, with an equation I equals Q over T. We'll also learn how to predict the products of the electrolysis in this process as well. For the electrolytic cells, we are forcing a current through a cell to produce a chemical change for which the cell potential is negative. So if you remember, we would have a positive delta G in the situations where the cell potential is a negative value, and so that would mean that it would not happen on its own. So energy must be supplied, in this case electrical energy, must be supplied to the reaction in order to make it take place. We use this process as a way to separate ores from each other in played out metals. So if you've ever heard about like chrome bumpers on old cars, that's the plating process that they would use to make the chrome metal on the bumpers. There's a couple of very important differences between the voltaic or the galvanic cells and an electrolytic cell. Number one, the voltaic cells, again, are spontaneous or thermodynamically favorable, and the electrolytic cells are forced to occur by using an electron pump or a battery or any direct current source, DC source. The voltaic cell is separated into two half cells to generate electricity. An electrolytic cell can occur in a single container. It can occur in multiple containers, but more often than not, it happens in a single container. So from a visual standpoint, with the diagrams for the cells, that's a very easy way to differentiate between the two. A voltaic or galvanic cell is a battery, and an electrolytic cell needs a battery. You still have the oxidation occurring at the anode and the reduction occurring at the cathode, but the polarities of the electrodes get reversed. The cathode will become a negative and the anode becomes a positive. So you can remember EPA, electrolytic positive anode. The electrons will still flow from the anode to the cathode. And usually, because we're dealing with solutions, they will occur using inert electrodes. Let's look at a quick comparison of voltaic and electrolytic cells. First off, your voltaic cells will have a delta G value less than 0 and will have an E cell value of greater than 0, meaning again that they are thermodynamically favored processes. The electrodes, you have the anode where oxidation occurs, and the polarity of the electrode is a negative value. The cathode is your positive electrode, and it will be where reduction takes place. So you still have the anox and the red cat coming into play here. For your electrolytic cells, you would have your delta G value being greater than 0, your electrochemical cell value being less than 0. So you'd have a negative value for E cell, positive value for delta G, which means a thermodynamically unfavored process. Your anode is where oxidation takes place, so it still has the oxidation at the anode, but you should hopefully notice again that the sign for the electrode has now switched to a positive. The cathode is still where reduction takes place, but it is also switched signs to now being a negative. I'll explain why that is the case in just a few moments, but also just kind of remember the last part of that is our relation to K. So I'm going to pop this in here, and our K value in this situation for your electrolytic cells, your K value would be greater than 1. and your electrolytic cells, your K value would be less than 1. All right, so now we're going to look at the electrolysis of water. During this process, you can see that we have bubbles of H2 gas and O2 gas that are forming, but please notice the difference in the amounts. Stoichiometrically speaking, we have approximately twice as much of the hydrogen gas that is formed compared to the oxygen gas. When we look at the processes that are taking place, the oxidation half reaction within this cell is 2H2O forming 4H plus O2 and 4 electrons being released. Notice here again I have 4 H pluses, so one of the little signature pieces that you could see for where the oxidation is taking place in that electrolytic cell is to look for a lowering of the pH. So the pH will go down in the oxidation half reaction as the concentration of H plus increases. When we look at the reduction half reaction, I have 2H2O plus 4 electrons forming 2H2 gas plus 2OH minus. So again, at this point where we have the reduction taking place, we could see an increase in the pH of the cell as well. Now, just understand these will not correspond to regular standard cell potentials, because in order to be standard cell potentials, remember the molarity of the solution has to be 1.0 molar for those standard conditions. I'll write that down here real quick. So your standard conditions would be 1 molar. However, in this particular instance, since we're talking about pure water, remember from our acid-base unit, the H3O plus and the OH minus concentrations initially, so I'll put the little initial sign there, would be equal to 1 times 10 to the negative 7th power, because we're talking about pure water. So as a result, we would have to use the Nernst equation to essentially figure out what the cell voltage would be for that particular reaction to take place. Because of the fact that it has such small ion concentrations, we also have to have some type of salt that can be added, or some type of electrolyte that will be added to the solution that will not be able to undergo one of those processes. So an example for the electrolyte that could be used would be the Na2SO4. When you think about those two ions, I have the Na2 plus and I have the SO42 minus. The Na2 plus, or the Na plus, that could theoretically add an electron and go to sodium as a metal. However, again, we would know that this would not occur because the amount of electricity that would be needed to reduce it will be greater than the amount that is required to reduce the water. And so that reaction would not take place. Hopefully that makes sense as well, because if I had solid Na forming, we know how reactive that is with water, and we would have an explosion with the sodium reacting with the water to form the sodium hydroxide. So we know that that would not be able to take place. And then the same type of thing, the SO42 minus is already at its maximum oxidation, because if you think about sulfur in the sulfate ion, it's already a +6 for its oxidation number, and so it's run out of valence electrons that it could theoretically give away. So you always want to find some type of salt or ionic compound, acid, that could be placed into that solution that would allow the electricity to flow through easily, but not actually have a chance of reacting in the mixture. We'll now take a look at the tin copper reaction and compare the process as a voltaic cell compared to an electrolytic cell. So you'll notice in this first diagram on the left, we have the voltaic cell that is present, and inside of that voltaic cell, for our basic sketch of the diagram, we have the tin solid for the anode that is undergoing oxidation, and it will produce the Sn2 plus ions into the solution. Notice initially we started off with a 1 molar concentration, but as the reaction progresses, you will see an increase in the concentration of the Sn2 plus. So again, think about the Nernst equation, and how as that concentration would increase, it would cause the E cell of the compartment to begin to lower. And that's because as it increases and the copper will decrease, you will see a overall lowering of the E cell value until it reaches equilibrium, at which point it would be dead. For the reduction, we have the copper 2 plus ion reacting with 2 electrons to form copper as a solid. So remember, the cathode is going to increase in its mass as the reaction progresses. And you can see here that, again, the concentration of the copper 2 plus ion in the solution would decrease. Now, the overall reaction that we would see for this thermodynamically favored process, where we would have 0.48 volts of energy produced, we would have Sn as a solid plus Cu2 plus aqueous forms Sn2 plus aqueous and Cu as a solid. Now let's shift gears and focus on the electrolytic cell. When we look at the electrolytic cell, again, we have the process being reversed. Notice that it says that we have an external source, so that would be my battery or direct current that is being applied, electron pump, however you want to term it, but that is going to be supplied right here, and so the electrons still flow in that fat cat format from the anode to the cathode, but it's just a little bit different. And I wanted to take a moment to just kind of explain why we see the polarities of the electrodes become the opposite of what they are for the voltaic cell. So in the initial galvanic cell or voltaic cell, you have a buildup of electrons that are occurring on the anode, which makes them have that positive value. And you notice the direction of the electron flow still from the anode to the cathode, but you'll notice that since the poles are being reversed, the flow of the electrons changes direction. So I still have the tin being the receiver of the negative charge, because it has the excess of the electrons that are going into that electrode initially. So when we look at this here, that external power source, again supplying the electrons with a voltage greater than 0.48, 0.48 would be that minimum threshold that would be required to make the reaction go in the opposite process. At 0.48 volts, hopefully you would remember the delta G for that process would be 0, and we would have a equilibrium type of situation. So once we put it greater than 0.48 volts, now we're forcing the electrons to go back into the opposite direction. So as I have this buildup of the electrons into the wire, now it's going to take the Sn2 plus ions out of the solution as they come in contact with those electrons, and they will now start to plate onto the tin electrode. At the same time, you're going to have the copper that is going to begin to go into the solution. So now the copper ions will decrease their concentration while the tin increase. And as that process takes place, the electrons will then flow through the copper anode and will go back towards the power source. So you still have that flow of the electrons from the anode into the cathode, but again, we're flipping the signs on those electrodes. So when we look at the different half reactions for that electrolytic cell, the oxidation half reaction, that's going to be the copper being oxidized into the Cu2 plus and the 2 electrons. The reduction half reaction will have the Sn2 plus 2 electrons forming Sn as a solid, and that will give us an overall reaction of the Sn2 plus the Cu forming Sn as a solid and the Cu2 plus ions. So you'll notice it's the exact opposite process that we had from the voltaic cell for that particular reaction. We're next going to look at a multi-billion-dollar process that occurs in industry all the time, and that is the electrolysis of pure molten salts. This is a way to separate the components of your salts, typically your very active metals, which are very hard to get alone by themselves. If your salt is pure, predicting the products is a very straightforward process. The cation is going to be reduced because we're going to force the electrons back into the cation, and the anion is going to be oxidized. The electrolyte is the molten salt itself, and the ions are attracted by the oppositely charged electrodes that are placed into the liquid. If we consider the electrolysis of molten calcium chloride, you can see here that the chloride ions as a liquid will go to chlorine gas plus 2 electrons. So you see that the anion is undergoing oxidation, and the calcium liquid, the calcium ions as a liquid plus 2 electrons form calcium as a solid. So you have the cathode undergoing the reduction, and that gives you an overall process of the Ca2 plus as a liquid plus the 2Cl minus as a liquid, forming Ca as a solid and Cl2 gas for the overall reaction. So this is one of the most important types of processes that we have to prepare your very active metals such as calcium, magnesium, sodium, and a lot of your halogens, chlorine and bromine as well. So now we're going to look at a mixture of molten salts. So in this type of situation, we will have the electrolyte as a mixture of molten salts that are being electrolyzed to obtain one of the metals. How we can tell which of these species will react at which electrode? It's pretty simple. The general rule for the electrolytic cell is the more easily reduced species, the stronger the oxidizing agent, that will react at the cathode. So when I look at my different values for the reduction potentials, I'm going to choose the one that is the more positive value because again, that is going to allow the substance to be more easily reduced. When I look at the more easily oxidized species, that is going to be the one that's going to react at the anode. Now, unfortunately, we can't use the standard E-cell values to tell the relative strengths of the oxidizing and the reducing agents, and that's because those are referring to the reactions taking place in aqueous solutions. So therefore, it's the water that is causing the ions to become free from the metal compound, and so we would have in that situation, under the standard state conditions, you'd have a certain amount of value that would be present to bring back that aqueous ion into the solid. However, we can look at periodic trends for the prediction of which ions will gain or lose the electrons more easily. So in the situation where we do not have the aqueous ions taking place, when we're looking at the metals, we want to look at their ionization energies, and whichever electron is going to be held more tightly, that is going to have the higher ionization energy, and if it holds on to the electrons more tightly, then it will be more easily reduced and it will form the solid much more readily. If you have a very low ionization energy, remember that means that it does not require much energy at all to remove the electron from the atom, and so it would very easily undergo the oxidation process. So we want to look for high ionization energies for the metals, and then if we have the anion, the nonmetal, we want to have its electrons being held less tightly by the atom. So when we're looking at the nonmetals, we want to focus on the electronegativity values. And remember, that's a measure of the attraction force between two electrons that are being shared between two atoms. The higher the electronegativity value is for a particular nonmetal, the more strongly it's going to hold on to those electrons, and so it will not be able to oxidize as easily. So we want to focus on the lower electronegativity value for the anions because again, they will be able to release that electron more readily from the atom. So if we just do a quick summary of what product is going to form at the different electrodes, experiments have shown that elements that can be prepared electrolytically from aqueous solutions of their salts, the cations of the less active metals, including gold, silver, copper, chromium, platinum, and cadmium, are reduced to the metal. cations of more active metals, including those in group 1A and 2A, and aluminum from group 3A, are not reduced. The water would get reduced to H2 and OH minus instead. And that's because their values, the amount of energy that would have to be added into the system in order to get the different ions to go into their solid form, would require more energy being added into the system compared to how much it would take to reduce the water. So that's why they will not undergo that reduction process. The anions that are oxidized, we have a concept that we call overvoltage, which is going to, I'll spend some time in class going over that concept, but essentially you can just kind of think about the overvoltage occurring when you have gases involved in your reaction. And basically it's going to require some energy to convert the aqueous ions into gases. And so that extra energy is related to the activation energy. And so that means that you have a very high activation energy for that particular process to take place. And so it just happens that a lot of times some of those other ions can undergo the oxidation process, and the anions can undergo the process more easily than the oxygen can form from the water. And so typically the overvoltage, you're adding an additional 0.4 to 0.6 volts of energy into the system that's required to electrolyze the oxygen. And so something like chlorine can then just sneak in underneath that threshold value for the oxidation and will allow the substance to undergo the oxidation instead of the oxygen. The one exception to that is the fluorine, and again that gets into some of our periodic trends, atomic size, all that kind of good stuff. So the anions that are not going to be oxidized includes F2, and then your common oxo anions such as the SO4 2-, the CO3 2-, NO3 1-, and PO4 3-. And as I had mentioned previously when we were talking about the water electrolyzing, that's due to the fact that the central atom for those different polyatomic ions already has its highest oxidation state. So if it were to lose any more electrons, it would be coming from the core electrons in one of those inner shells. And so therefore that would require a tremendous amount of energy, much more than it would take to have the water undergo that oxidation process instead. So we're now going to get into Faraday's law. Just use dimensional analysis and you'll be fine. But we're going to use this to look at the plating of metals onto some type of electrode. The amount of the substance that's being oxidized or reduced at each electrode during electrolysis is directly proportional to the amount of electricity that's passing through the cell. So we know by definition that 1 volt is equal to 1 joule per coulomb, and 1 amp is 1 coulomb per second. We measure current in amps, but it's symbolized as an I. So that equation that I was talking about at the very beginning, that's where the I is coming into play. We have the Faraday's constant, that is 96,500 or 485 coulombs per mole of electrons. So the basic process that you want to go through to solve these problems is you want to figure out your quantity of the charge, that's your coulombs. That's also where, again, you need to have your end value from your balanced half reaction. So, or your balanced redox reaction. So we'll put that here. So we have that from our balanced redox reaction. Okay, so again, we use Faraday's constant to convert that into moles. So again, taking your current times time, that will get you your quantity of charge in coulombs. And then you can use the Faraday's constant to get that into moles of the electrons. You can use the N from your balanced half reaction to figure out how many moles of the substance were oxidized or reduced. And then from there, you can use your molar mass to determine the grams of the substance that it will be oxidized or reduced during that certain amount of time. Let's now look at an example problem for Faraday's law by calculating the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 amps. A couple things within this problem. Notice that it is molten aluminum chloride, so it is not aqueous. It is going to be just the melted aluminum chloride, so the ions themselves would be the electrolytes. I have 10 amps involved in this process, and remember that that would be the equivalent of saying 10 coulombs per second. And we have hours that are given to us for the time. So use dimensional analysis for these problems, and it will be very easy to solve. The other thing that we need to do just as a starting point is get the reduction equation for the aluminum, so we know the number of electrons. So I know that I have aluminum as a 3+ charge, going to have 3 electrons added to it, and that will produce aluminum as the solid for the electroplating process. So I now have my value for N equaling 3. So we're now ready to start. So I can use the 10 coulombs per second as a conversion factor. So the first thing I want to do is start with my time. So I would have 1 hour for the time. And I know that for every 1 hour, we'll just simplify it and say that there's 3,600 seconds instead of doing the 60 minutes and 60 seconds in a minute. So we can now look here at our conversion factor. So I would have the 1 second uses 10 coulombs of charge. And now at this point, if you followed along the little concept map progression, I can now use the Faraday's constant, 96,485 or 96,500, depending on what they give you on the AP exam. But that is the number of coulombs for 1 mole of electrons. And now at this point, we can use this and we can say that we have 3 moles of electrons that are consumed for the production of 1 mole of aluminum. And to solve for grams, the molar mass of the aluminum will be 26.98 for our grams. And so now at this point, we are getting approximately 3.35 grams of aluminum. All right, so now let's talk about the corrosion of metals. So we're going to look at the corrosion of iron as an example. So first off, when we're talking about the corrosion of a metal, it is an electrochemical process. And basically what it's doing is it is involving oxidation to return the metals to their natural state, which is one of their ores, or minerals. So when they are involving that process, they're going to lose their structural integrity, they're going to lose their nice attractive look for the metals, and they're going to look like they are about to fall apart in many cases. So we're going to deal with iron as it's one of the most common ones that we see. You think about if you have ever lived up north, you'll know this. In the wintertime, again, they're always putting salt on the roads to help prevent the freezing up of the water on the roads. And so a lot of times what you'll find is that the cars that are up north are going to have a layer of corrosion along the bottom of the doors, where you'll start to see the rusting of the doors on the edges because of all the salt that is present inside of the water that is being splashed up onto the bottom of the car. And so when you have the corrosion that is taking place, basically the steel surface is not completely smooth. It's got not homogeneous because it's an alloy, so it's going to have different regions that have some stress points within the metal surface, and that's going to cause the iron to be more easily oxidized at some point, which we would talk about that being the anodic region. And then it has others where the ore will start to build up, where it will form the rust at the cathodic region of the space. So when we are looking at these different scenarios here, what you will find is that the iron, as it gets dissolved in the solution, will migrate over towards where the rust is and or is starting to form, and it will deposit it as the iron 3 oxide on the edge of the metal surface. So when we are looking at the region here, you can see this cathodic region where we have the oxygen undergoing the reduction process to form the O2 minus ion, and then you have the Fe that is in this little pit or the little dent that has been caused on the surface of the metal. You're going to find that that will, again, like your anodes, you would see that the mass is starting to eat away. So you would have that region of space where the iron is going into the solution, reacting with the oxygen that's present, and forming the rust on the outside edge of the water. And so you end up having that weakened spot where the corrosion is taking place. So the last thing that we're going to discuss is the use of sacrificial anodes to prevent iron corrosion. So basically what that means when we have a sacrificial anode is they're going to use a more active metal, and that more active metal will undergo the oxidation process instead of the iron. So it's easier for the other substance to undergo the oxidation. And so think about your electrochemical potentials. It is easier for those substances to undergo that process, so they will undergo that process instead of the metal. So it's used as a way to protect the iron inside of the ground in this case, for it to not undergo the oxidation process, and it will keep its integrity for a longer period of time. The magnesium rod that they're using in this case for the pipes, the magnesium has a much larger oxidation potential, or much lower, more negative reduction potential than the iron has, and so it will be much more readily undergoing oxidation as a result. You've seen this before if you've heard the term galvanized for nails. They coat the nails in zinc, so that way the zinc on the outside will undergo the oxidation process, and it will protect the iron that's on the inside of the nail. So it will make it a much longer lasting nail, so that way it can hold up whatever structures it's being used for a much longer period of time. And then finally, you also, if you've ever been on a cruise or on a large ship before, whether it's for a cruise or if it's like a cargo ship or something like that, you would find that underneath the hull you would also have these huge large rods of magnesium that would be down inside, because if you've ever again lived up north and know the effect of salt water on the corrosion of the metals, by having the magnesium bars tied into the hull of the ship, the outside of the ship, that will protect the outside of the ship, the iron, from undergoing the oxidation, and it will have the metal bars on the inside that would get eaten away through time from that electrochemical process, and again protecting the integrity of the ship, making sure that there is no corrosion on the outside of it, and providing weak points where the water could then rush in and sink the ship. So that is your basis for your sacrificial anodes, is that it allows the metal for the casing of whatever we're looking at, it allows it to be protected for a much longer period of time, so that its integrity stands. So that wraps up this last video covering the electrolytic cells. We'll spend some more time in class doing some practice problems, and I'll take any questions that you guys may have. So you guys need to just read over the little section on batteries in your textbook for the different types of batteries. We'll talk about the down cell and the Hall-Héroult process for the refining of aluminum from its ores, and we'll talk about that in class tomorrow. But other than that, have a wonderful evening, afternoon, whenever you're watching it, and I will see you guys tomorrow.